Hello everyone, myself Professor Tushar Gujrati from SNT College of Engineering, Yevla. Today we'll study the control systems but in composite modes. Okay, so as we have seen earlier videos that we use the control actions differently also, but if we want to overcome the advantages and drawbacks of each control, then we have to use composite controller modes. Okay, so here we are understanding PI and PD control mode. Okay, so actually to take advantage of the merits of each of this mode and at the same time eliminate the drawbacks to some extent, different modes of controls can be combined. Okay, so such a modes of control are called as composite modes of control. So here we are watching now PI and PD control modes. So here this is parallel form of PI control. So PI means proportional integral control. So proportional mode can be additively combined with integral mode to get the benefits of both the modes. Okay, so this is called as proportional integral controller. So here mathematically it is shown h of s. This is the transfer function of the PI control. So here we have to add both the transfer functions kp plus ki upon s. Kp is transfer function of P controller and Ki upon S is transfer function of derivative controller, integral controller. So combinedly we get H of S. Okay, so here in this equation Kp is proportional gain and Ki is integral gain. Okay, so, and if we write equation of output U of t is equal to, then it will be addition of both the outputs up of t plus ui of t. Okay, so it is up of t, it is kp into e, proportional constant into error, plus ki into integration of e dt. So this is the equation of output. So what is written here? Proportional integral control helps minimize rise time, settling time, as well as eliminate steady state error. Okay, the steady state error is present in proportional controller, we know that. So this can be eliminated with the help of integral controller. Okay, and with the help of proportional mode we can minimize rise time and settling time also. So like this we got advantages of both the controllers at the same time. So like this it is shown. The first graph indicates the error signal, and in the second graph how the overshoot is controlled and how the system gets stable earlier, that is shown. So in the second graph you can see that overshoots are decreased as well as settling time is also decreased. Okay, so like this PI control action works. Now we'll try to understand what is PD control action. Okay, so as we know that a derivative control action may be additively combined with proportional control. So here derivative control action is additively combined with proportional control. In fact, as we know that derivative control is never used alone. We cannot use derivative control alone. It should be always used in combination with other modes. Okay, that's why we have combined it with proportional mode. So now here the transfer function is h of s is equal to kp plus kd into s. So kp is transfer function of proportional mode and kd into s is transfer function of derivative mode, and where kp is called as proportional gain and kd is called as derivative gain. So here the control signal is u of t is equal to addition of both the signals, proportional and derivative, and finally we get equation as kp into e plus kd into de by dt. Okay, so this is the control action equation. So what is written here? Proportional derivative control helps to reduce rise time, settling time, as well as minimize overshoot. So overshoot can be minimized as well as rise time, settling time are also minimized. So this is the advantage of this composite control mode. Now you check the diagram again. First diagram indicates overshoots are there and rise time, settling time is also more, but in second time diagram overshoot is decreased. Okay, and we got system stable, but there is little bit error is present. You can see that there is little bit error is present, steady state error is present. Okay, so like this the combination of proportional and derivative control can work. So here one graph is shown, that is comparative graph is shown, that is response of P, I and D with respect to error. So what is the response of P, I and D with respect to error? Suppose error is varying from 0% to 5% to 10% in the first graph. So if only proportional action is working in the second graph, if only proportional action is working, then we'll get a proportional curve like this. So we'll get just proportional curve. And in this only way added reset action, then what will happen? It will get some curve. Okay. So if reset action is added, then we'll get curve. So reset action means nothing but it is integral action. Okay. So that's why we'll get curved. If rate only action, rate means if we are using derivative action, then what will happen? We'll get stepped output. Okay, like this we'll get output. And if we add proportional plus rate output, then we'll get step also and some curvature also. Okay, so like this, if we combine everything, we'll get step as well as curvature. So like this, we will get different control actions if error is varying for 3 different type of controllers. So from this you should understand that what type of control action you want in the your particular application. Suppose in the particular application you want such a stable output, at that time you can go for derivative. If you want like this curvature output to be controlled continuously increasing, at the time you go for integral. If you want both, then you can go for proportional per plus rate output. Okay, so like this you can select particular control action depending upon your applications. So here one table is shown, summary table. So effect of P, I and D control on transient specifications. So actions are shown here, Kp, Ki and Kd. Okay, so Kp, Ki and Kd, these are different actions. So if you use Kp, what will happen? Rise time decreases, overshoot increases, settling time is small changes, steady state error decreases. So these are the advantages of Kp. When you use Ki, then you can reduce rise time, you can eliminate steady state error, settling time decreases then increases, and overshoot increases. When you use Kd, there is small change in rise time, overshoot decreases, settling time decreases, and steady state error has small change. So like this, every action Kp, Ki and Kd, there is some advantages, disadvantages. Okay, that's why we have to use this in combined mode, composite mode. Okay, that's why we go for composite modes. So who eliminates steady state error? If I ask you one question, which type of control action reduces or eliminates steady state error, then it is Ki. Ki completely eliminates steady state error. Now I will ask you one question, which control action decreases the overshoot? It is Kd. So derivative control action decreases the overshoot. Which control action decreases settling time? So this Kd decreases the settling time. Okay. And which type of control actions decreases the rise time? So this is Kp, and Ki decreases the rise time. Okay. So like this you remember the advantages of these different control actions, and then you can combine them. Okay. So here all the control actions are combined. Suppose P, I and D all are combined. Then you see in the first graph, you will see very large overshoot is there. So this large overshoot is reduced in the second diagram when we use PID control action. So there is small overshoot is present and the system is stable. That is, error is also reduced completely. It is the output line is along one point. Okay, that's why there is error is also reduced, overshoot is also reduced, and settling time are also reduced. Okay, so like this PID control action works. So the values of Kp, Ki and Kd, Kp, Ki and Kd are manually adjusted, okay, in particular PID controller. So that is called as manual testing of manual tuning of PID controller. It is called as manual tuning of PID controller. So there are some steps are shown. So first step is obtain an open loop response and determine what needs to be improved. So in the first step, we have to assume as an open loop system and we should determine what needs to be improved. Then in the second step, add a proportional control to improve the rise time. We have to add proportional control and we have to increase the improve rise time. Then add derivative control to improve the overshoot. Add an integral control to eliminate the steady state error. So these are the steps. Adjust each of PID until you obtain a desired overall response, referring to the table shown previously to find out which control what characteristic. So here we have to adjust the values of P, I and D. In the system, the values are already available. Setting is available. We can change the values of P, I and D. By changing the values of P, I and D, we have to try to achieve the desired output. And last point, it is not necessary to implement all the three controllers into a single system. For example, if a PI controller gives a good enough response, then you don't need to add a D control system. Simple is better. Okay, this you remember. What is simple is better. If PI gives you the total control, then you should not go for adding D option also. Okay, so like this, by adjusting values of control actions P, I and D, we get the desired controlled output. Okay, so you should note here, one note is given, it is not necessary to implement all the three controllers P, I and D into single system. So there is no need to implement all the three controllers. For example, if a PI controller gives a good enough response, then you don't need to add D control to the system. Simple is better. So understand this simple is better concept. Okay. So what is written here, 90% processes are controlled using PID. So 90% processes are controlled using PID, means adding all the three control actions, like regulation of process in industry. For example, if you want to regulate the flow, if you want to regulate temperature, pressure, so these can be regulated with the help of PID controllers. Servo/DC motor control also can be done with the help of PID controller. Linear position control also can be done with the help of PID control action. So these are some applications of PID controller. So thank you so much all of you watching this video. So in this video we covered the PI and PD composite control modes. We have seen their graphs, how they can be controlled, and finally we studied how we can do manual tuning of the PID controller. So thank you so much all of you for watching this video. In the next video we'll try to cover this tuning of PID controller in detail. Okay, so thank you so much.